In November of this year, we released a video about the quantum computing industry. In the video, we explained the numerous practical challenges associated with this technology. Today's quantum computers are not capable of performing any useful task, and we are skeptical that this will change in the near future. Just a few weeks later, on December 9, 2024, Google claimed to have achieved a breakthrough in quantum computing. Here's a short clip Google posted on one of its YouTube channels boasting of this achievement.
By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe. This result highlights the exponentially growing gap between classical and quantum computation for certain applications. Looking to the future with Willow, we continue our journey towards building large-scale and useful error-corrected quantum computers that will push the boundaries of science and the exploration of nature. With future commercially useful applications in areas like pharmaceuticals, batteries, and fusion power, we are excited to solve the otherwise unsolvable problems of tomorrow.
Their new Willow quantum computer can perform a computation in less than 5 minutes that would take the world's fastest supercomputer 10 septillion years, which is longer than the age of the universe. This claimed breakthrough has resulted in breathless coverage in the media.
Shares of Google jumping today after announcing that quantum computing breakthrough, saying that its new chip, Willow, can perform a milestone computing task in just 5 minutes and would have taken a classical supercomputer longer than the history of the universe to do.
It's a technology that could transform everything from AI, cybersecurity, scientific research, to even financial strategies.
Was right. I don't know if you remember The Matrix and Neo at one point who is going to discover the Matrix. It's going to be this sort of rain of zeros and ones around it. Well, this is what quantum is telling us, that maybe we're living in something closer to a multiverse of parallel worlds.
It's not just the media hyping up the mystical aspects of quantum computing. In a press release, Google itself suggests that its quantum computer may be operating in many parallel universes, in line with the idea that we live in a multiverse. I never thought I would live to see the day where a Fortune 500 company unironically claims to be harnessing the power of the multiverse. In this video, we'll take another look at the world of quantum computing, specifically in light of Google's recently claimed breakthrough. Performing a calculation that would take the world's fastest supercomputer longer than the age of the universe certainly sounds impressive, but it's important to understand the nature of this computation. Here's Google's head of quantum, Dr. Hartmut Neven, explaining just that.
We should emphasize that random circuit sampling is not useful for an application. It's just the entry point. If you can't win on random circuit sampling, you can't win on any other algorithm either.
The Willow quantum computer did something called random circuit sampling, which he admits has zero practical application. So what is random circuit sampling, and why do they do it if it has no practical applications? The quantum computer is made up of qubits. The qubits exist in a state of superposition, where they are both 0 and 1 at the same time. The qubits exist in a state of entanglement, where the state of each qubit impacts the states of all other qubits. Upon observation, the qubit collapses to either 0 or 1. You program the quantum computer to manipulate the probabilities of each qubit. You then observe the qubits. Every time you observe the qubits, you get a string of random numbers. If the quantum computer is working as intended, the strings of random numbers should fit within the probability distribution you programmed. When you write the program, you know that certain strings should be more likely than others. For example, let's say you program the quantum computer such that this string should happen more often than this one. You run the program 1,000,000 times, and check whether you indeed generated more of the more likely strings than the less likely ones. You can use a classical computer to simulate what a quantum computer would do. As you increase the number of qubits or the complexity of the instructions, the interaction between the qubits becomes exponentially more complex, and thus more difficult to simulate on a classical computer. The qubits need to be isolated from outside interference. Google uses superconducting qubits, which need to be kept at extremely cold temperatures, almost absolute zero. The more qubits you add and the longer the quantum program takes to run, the more likely that outside noise will contaminate the qubits. If there is too much noise, the random strings you generate will not be correlated with the probability distribution you expect. Every quantum computer is noisy. But remember that you're generating random strings millions of times. Of these millions of samples, the vast majority of them will be noise, but a few of them will indeed be created by the instructions you programmed. The goal is to get the noise low enough that you can detect the signal through the noise. If a quantum computer is very small, it won't have that much noise, but its quantum interactions are also not very complex, so it can be easily simulated by a classical computer. As you increase the size of the quantum computer, it becomes more difficult for a classical computer to simulate it, but it is also much more prone to noise. Google's goal was to make a quantum computer big enough that it can't be simulated by a classical computer, while also being robust enough that its output is not completely drowned out by noise. They indeed achieved this in 2019. With their Sycamore quantum chip, they did a random circuit sampling exercise, which they claimed would take the world's fastest supercomputer 10,000 years to simulate. If the distribution of the random circuit sampling is so complex that it cannot be simulated on a supercomputer, how can we verify that it worked? There are mathematical methods to determine whether the output of the quantum computer is similar to what you expect. The technicalities of how this works is beyond the scope of this video. What Google showed in 2019 is that they have at least some control over the qubits, and there are so many qubits that it would be impossible to simulate on a classical computer. Many companies have developed quantum computers, including Google, IBM, and numerous startups. But in my opinion, it's a bit misleading to call any of these quantum devices computers. To be a computer, you have to compute something. For example, an abacus is a computer. You can perform basic arithmetic on it, something that today's quantum computers cannot do. I will argue that a paper airplane is just as much of a computer as today's quantum computers. Let's suppose you go up to the top of a skyscraper during a windy day. You throw a paper airplane off the edge. Many factors will impact how the paper airplane will fly. The wind conditions, humidity, the exact shape and weight of the paper airplane, etc. If you knew all the initial conditions and imputed them into the right software, you could simulate the path of the paper airplane and predict exactly where it will land. This simulation needs to be very precise, as a slight change to any of the conditions will change where the airplane lands. This might be very difficult to simulate. It might even take the world's largest supercomputer 10 septillion years. Or you can just make the paper airplane and throw it from the top of the skyscraper and see where it lands. This would be much faster than trying to predict where it will land via simulation. But it would be absurd to say that the paper airplane is more powerful than the world's fastest supercomputer. A paper airplane is obviously not a computer. I argue that today's so-called quantum computers are more similar to paper airplanes than actual computers. The qubits are interacting with each other in a manner that is difficult to simulate on a classical computer. But you're not actually computing anything. You're just sampling a bunch of random numbers that the qubits spit out. Quantum computers will never replace classical computers. You will never be able to play video games, browse the web, or even perform basic arithmetic on a quantum computer. The main envisaged use case of quantum computers is to simulate quantum phenomena. In Google's promotional video, they talk about eventually using quantum computers in drug discovery, developing new batteries, and nuclear fusion. The idea is that you would set up the qubits to simulate molecules and how they interact on a quantum level. The quantum properties of the qubits simulate quantum properties in the real world. To perform commercially useful simulations, you need the quantum computer to receive instructions that are far more complicated than what they can handle today. Today, they can only do random circuit sampling, which has zero practical applications. Google already achieved so-called quantum supremacy with its Sycamore chip in 2019. Sycamore had 54 qubits. They performed a random circuit sampling exercise that would have taken the world's fastest supercomputer 10,000 years to simulate. In 2024, they unveiled their new quantum chip called Willow. Willow has 105 qubits and performed a random circuit sampling exercise that would have taken 10 septillion years to simulate on a classical computer. Willow did the same thing that Sycamore did, just on a bigger scale. So why is Willow considered to be such a breakthrough when it still can't do anything useful? Google claims to have made a breakthrough in quantum error correction. One of the ways to increase the accuracy of a quantum computer is to combine multiple qubits into groups. These groups of qubits are called logical qubits. There are ways to indirectly observe groups of qubits and correct for decoherence on the level of the logical qubit. This is called error correction. Adding more qubits allows you to do error correction, but each additional qubit also introduces its own noise. For the quantum computer to scale, you need to get the noise of each qubit below a certain threshold, such that the benefit from error correction more than offsets the additional noise from adding more qubits. Google claims that Willow achieved this threshold for error correction. Thus, going forward, the more qubits they add, the more accurate will be the quantum computer. This claim has not been peer-reviewed or verified by anybody outside of Google, but let's just take their word for it. If they have indeed achieved the error correction threshold, how close does that get us towards practical applications? There's no better person to ask than Dr. Hartmut Neven, the head of Google's quantum lab.
After the 2019 result, we published a roadmap how to get to what we think will be a quantum computer that can confidently deliver commercial value. And we packed it to be a computer with 1,000 well-protected logical qubits, which probably means about 1 million physical qubits. And we published a roadmap how to get there. It has 6 milestones, and we are now approaching the third milestone. So we are about halfway through our roadmap. And we are not much delayed relative to what we say the timeline would be. So I've said this before, my subtitle here is Chief Optimist, but I think just tracking our progress date is that we should see early commercial applications. So I would think it's more half a decade or a few years rather than multiple decades.
In 2019, they had a quantum computer with 54 qubits. 5 years later, in 2024, they have 105 qubits. Dr. Nevin himself says they need 1 million qubits to deliver commercial value. So it took them 5 years to get from 54 qubits to 105. Now he's saying in another 5 years they'll get to 1 million. This timeline is a little difficult to believe. To be clear, we don't even know if a hypothetical 1 million qubit device would even be capable of performing useful computations, as no such device yet exists, nor can it be simulated on a classical computer. The idea that a 1 million qubit quantum computer can deliver commercial value is a speculative conjecture. Quantum computing sounds cool to laypeople. Its potential has been breathlessly hyped up by the media for many years. Google's recently proclaimed breakthrough has added fuel to the fire of cringeworthy hype. In Google's press release, they said Willow performed a computation that would take today's fastest supercomputer 10 septillion years. As we discussed earlier, I think it's debatable whether the random circuit sampling can even be considered a computation, but whatever. Google explains that 10 septillion years vastly exceeds the age of the universe. This lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse. I have no idea whether or not we live in a multiverse, but you don't need a PhD to see that this argument is logically flawed. Google would have you believe that its quantum computer is so powerful that its immense computational power can only be explained by borrowing power from parallel universes. The fact that the computation would take longer than the age of the known universe is evidence that such an awesome computation cannot be achieved without the help of the multiverse. To show how absurd this line of reasoning is, let's extend it to a MacBook Air. Let's say hypothetically that you build a time machine and go back 300 years into the past. You bring your MacBook with you. 300 years ago, the world's most advanced supercomputer was an abacus. I'm sure you could find some computation that you can do on a MacBook in 5 minutes that would take 10 septillion years to do on an abacus. Does this mean your MacBook is performing computations in parallel universes? Of course not, it's just a regular computer. The speed of the world's fastest supercomputer at any given time is arbitrary. This metric changes over time as more advanced supercomputers are developed. The 10 septillion number Google talks about is a man-made metric that has nothing to do with the laws of physics or the supposed multiverse. Given that Google is willing to make such an absurd and logically nonsensical argument about parallel universes, I find it difficult to take anything they say seriously. Alright guys, that wraps it up for this video. What do you think about quantum computing? Let us know in the comment section below. As always, thank you so much for watching and we'll see you in the next one. Wall Street Millennial, signing out.